Okay, I'll begin first with introduction again. My name is Oded Paz. I'm from Mellanox. I'm working in Mellanox for 3.5 years about, and doing training. I'm part of a support division, which means we are involved in all the issues, if you like, and technologies that Mellanox is dealing with. Some of you might have met me maybe last year or 2 years ago, well, last year. And my main intention today is actually to provide the HPC experts, because you are actually HPC experts, to the guys among you which are not familiar with basics of InfiniBand, and the most important issues in InfiniBand skeleton, if you like, or fabric. I would like to make it clear to most of us. So this is my main intention today. I have an additional small target, and the small target is to provide you an information about Mellanox Academy. Mellanox Academy actually is an organization that can help you get different type of information. We still have problems with that? Yeah? Okay. So we would like to allow you to offer you training services that could be online services, that could be instructor-led training, could be also web training, or, okay, that's better, I suppose. And this is part of Mellanox Academy. So a lot of subjects that some of you have holes of knowledge in them are covered as part of Mellanox Academy. And as you can see, as I was saying, we are providing instructor-led training, which is me and some other people. We have online training, and we also have certification processes in order to allow people of your organization to verify that they have the right knowledge to provide support, or even just to verify that they have the basic of the InfiniBand technology in order to get most of that. So this is actually the Mellanox Academy. If you will enter to our Mellanox Academy, you will see that you have the white papers, you have videos, you have simulators, and you have other tools that can help you get theoretical knowledge as well as practical knowledge if you are going into configuration or installation sessions. So our sessions does not force you to take, again, instructor-led training. You can also do a lot of jobs by taking the e-learning sessions. I'm not going to go into the specific solutions that are provided. Actually, I told you what we are providing. And as I was saying, we have different types of learning methods, instructor, web, e-learning, and those are the main ones. We have a list here of the offering, a list of the training that you can have. So, of course, you don't have to take it now, but you need to be aware that you have that option. And as we were saying, we have flexible solution, a unique solution for all knowledge levels and professional roles in the InfiniBand environment, and InfiniBand and HPC as well. We have varied content of sessions and courses, and we have also flexible payment options. But between you and me, money is not a problem, so I suppose you don't care about that. Of course, we have certified remote lab instructors and coursework that you can use for that matter. So We really urge you to use Mellanox Academy, not for maybe your own personal use, but your environment and your partners. And this is about the Mellanox Academy. This is the site, by the way, of the Mellanox Academy. Maybe try to use it later and see what are the options. And that was my introduction regarding Mellanox Academy. And let's start with the main target that we would like to cover today. So the session is called InfiniBand Essentials. Every HPC expert must know. So you are already HPC experts. So I suppose you should know the following subjects. Some of you are familiar with all of them. Some of you are familiar with nothing. Some of you are familiar with part of that. Let's try to cover together, again, what we are going to look at the IB principles. We are going to talk about the fabric components, the network components, and the fabric architecture. We are going to talk about the network or fabric discovery, mainly the jobs of the Subnet Manager, which is in charge of basically everything in the network. We are going to talk about the main things that happens and the main functions of each one of the InfiniBand protocol layers. And we'll talk a bit about Mellanox products. These are the things that I'm going to cover today. Of course, if you will have specific questions or questions that will arise during my sessions, you're free to ask. I hope I would be able to provide answers to all questions. And in case I won't be able, I promise to provide you the right answers by mail. Again, my name is Oded Paz from Mellanox. I'm not going to ask you for all your names now. It's beyond 20 people, so I'm not going to do that. But if you ask questions, I will be happy if you are able to present yourself. Where are you coming from? What is your job in the organization? Which organization, etc. Thank you very much. And we will begin. Something to ask before I begin? No? Okay. So when we talk about the InfiniBand environment, InfiniBand Fabric, InfiniBand Network are going to provide the best solution today, especially to move traffic, to move data in HPC environment. And the reasons are because it does provide 3 or 4 features that are very, very important for the users, for the customers, for the clients, for the applications of the HPC, the high-performance computing environment. If you look at the slide that we see here, then a network, usually a fabric, will have its clients. The clients will be servers that are compute servers or storage servers that have to move traffic between them. In order to provide the switching between them, we are providing the InfiniBand switches, which are working with the InfiniBand protocol. The connections between the compute nodes to the switches or the storage nodes to the switches are used with InfiniBand links. Those InfiniBand links today are going in a pace, in a speed of 56 gigabit per second, which is called FDR. We're going to talk about it later. And later this year, the maximum rate per port will reach 100 gigabit per second in a speed rate that is called, or standard, that each specific part is called the EDR, Enhanced Data Rate. So currently we are in the generation that allows us per port of a server and per port of a switch of up to 56 gigabit per second. If we talk specifically about the Mellanox technology, Mellanox technology generation today is providing the channel adapter on the server side, or the network adapter, what is called the HCA, host channel adapters, in a generation which is called Connect X3 and Connect IB. I'm going to talk about the differences between them. And the switches generation that do provide the FDR capability are called Switch X2. When you talk about the InfiniBand environment and InfiniBand technology, you have specific integrated circuits for that, ICs, or chips if you like. And in our case, Mellanox is providing and producing and planning those chips, which are part of the channel adapters and parts of the switches. As we were saying, we have the adapter cards that in the InfiniBand are called the host channel adapters of different types. We have different types because they provide different capabilities for different users and customers according to the need. And of course, we have different type of switches, and the most or the main reason for the difference between the switches will be the capacity. Capacity of ports, capacity of servers that each one of the switches may actually support. So we are talking about the switches options, or InfiniBand switches, that are going between range of 12 ports up to 648 ports for a specific switch. And then, of course, in order to allow us to enhance performance of customers, to enhance performance of applications, we also have different type of software solutions. Begins with management solution like the UFM, Unified Fabric Managers. We are talking about the FCA, which is now part of the standard, actually part of Red Hat, the FCA accelerator, or Fabric Collection Accelerations. We have VSA for storage, virtual storage accelerator, and other options that will help you actually, as part of your solution that you provide to your customers, to provide better latency, better performance, better usage of the CPU and hardware resources. Of course, part of the network usually will be the media. The media between the servers to the switches, the media are the cables. The cables are of two main categories, the copper cables and the fiber cables. This is the first category. Beyond that category of copper cables and fiber cables, we have the other category which talks about, is it a passive type of cable or active type of cable? Just to make it short and simple, usually when we are talking about the difference between passive cable and active cable will allow you to have a longer distance between two ends or two nodes in the fabric. So when we talk about the targets of Mellanox, targets of the InfiniBand technology today, we are talking about different type of applications like financial services, cloud, database enterprises, Web 2.0, and of course the most important is HPC. It will be different if I'm going to talk in the cloud environment, but for this session it's the HPC. This is the most important one. So we are talking about actually advantage and better performance, enhanced performance to the HPC environment when you are working with InfiniBand specifically, and of course with some of our Mellanox solutions that will allow you to provide 10 times better performance, higher usage or better usage of your CPU resources, better latency, and of course very high bandwidth from the server side to the switches side. In order to provide that, of course, we need different components in the network to be better. And this is actually the job of the technology, the job of the fabric, that will provide the service for you. So what we're going to see today is what are the basics again of the technology, what are the main components, what is their job, and how could we make it better. As I was saying before, in order to provide the main components in the network, Mellanox has the technology for the channel adapter, which is today in a generation which is called ConnectX-3. And in the switches environment, we are talking about Switch X2. Both of those guys are able to provide today FDR, 56 gigabit per second, per port of the channel adapter or per port of the switch. About the ConnectX-3, as you can say, ConnectX-3 will allow you to connect on the bus side, on the server side, to connect with PCI generation number 3. PCI 3 will be supported by ConnectX-3 channel adapter cards. Any question in this stage? No? Okay. So when we talk about InfiniBand generation, and InfiniBand planning, what is the plan ahead? What is the history of the InfiniBand? So InfiniBand as a network, InfiniBand as a pipe provider was planned in around 2000. And in around 2000, the port capability in the InfiniBand environment, it was huge for that specific period, we could have provided 10 gigabit per second per port, and the year was 2001. In 2005, we came to the second generation that was called DDR, double data rate, with a capability of 20 gigabit per second per port. The next generation that I suppose part of you are still working with was a QDR. QDR is able to provide 40 gigabit per second per port. Can you tell me who in the audience has in his cluster QDR? QDR. So 70% is actually still working with QDR. So can you also tell me what is the capability in data that every QDR port can provide, can support? How much data can you forward on every QDR port? You are pointing that, and this is, you're saying? 40 gigabit. What is your name? Gabriel. Gabriel. Gabriel is saying 40 gigabit. Do you agree? Well? 32. He's saying 32. Okay. So, well, QDR provides 40 gigabit per second of signal, you may say. So the signal, the bits, if you will count them, you will see 40 gigabit per second. But actually, we will see that in the QDR generation, we have encoding, which is called 8 by 10, that actually takes 20% of the line rate, if you like, and provide it for the overhead, encoding overhead. So this is the QDR generation. Part of you also have ports, channel adapters, and switches of the FDR generations. Who has FDR today? So we're coming to 10% FDR, 56 gigabit per second, and this is today. And if we are going to talk about the end of this year, I don't want to provide you specific dates, then we would be able to provide also 100 gigabit per second per port. And this is the new generation, or the current generation at the end of 2014, which will be the EDR generation, enhanced data rate, 100 gigabit per second per port of your server, 100 gigabit per second per port on the switch. Of course, the other element, the other parameter which is very important specifically for high performance compute will be the latency. How much time does it take for a packet, for a calculation, to go between one server to the other server? And this is actually the latency. The latency is the latency, when I'm talking here about the latency, what is the latency that I am as a switch? As InfiniBand switch, I'm going to add to the packet that comes into my switch and then goes out. I'm not going to talk about the latency that is actually happens, if you like, in the server. That happens in the process between the application, upper layers to the lower layers. I'm talking about the latency that is added by the switch. The latency that is added by the switch specifically, we will talk about it maybe again later. When a packet comes into InfiniBand switch of Mellanox in our example, until it goes out, every switch or every hop of a switch will add 170 nanoseconds. Of course, you can tell me, Oded, but usually we are going, when a packet enters to the fabric, many times it is actually passing more than one switch, more than one hop. It may go to the first switch, and then to the second switch, and then to the third switch. So how do you count that? Of course, I'm going to add the delay. So if I have a delay of 170 seconds in one switch, and then another one, and then another one, then I'm going to come for 500 to 700 nanoseconds of delay, which is still very, very short and good delay. And this is in the current generation of FDR. But what was the beginning of the InfiniBand? The beginning of the InfiniBand, 1999. There is an organization which is called, was set up an organization that was called the IBTA, InfiniBand Trade Association, founded in 1999. And the target of the IBTA was to provide the network and the protocol for data. So this is not something which is new. We already had networks like X25 and ISDN and Ethernet and fiber channel and frame relay. So all those networks are actually also providing data networks. So what is the difference? What is the main difference, or what is one of the main differences between data network of InfiniBand to the other data network? So first, it was created, it was thought about in 2000s. So in 2000, they were thinking already about customers of the 2000s, applications of the 2000s, performance, capacity, latency, application, HPCs that cannot work with the other protocols because they are too slow, because they are too narrow, and also because of another very important factor. One of the things that was not thought about in the other network, like Ethernet switching, they were not thinking about what happens to a packet of data, to a message of data in the server itself. When you are taking a packet of data in the TCP/IP environment, that packet of data is taken and then it is put into frames in the higher layers, and then it goes in the server to the kernel environment, to the TCP/IP kernel environment. And what happens there? That the kernel environment has to process each one of those packets. Each one of the data packets has to be processed in the kernel environment, and then to be sent, to be copied to another buffer, and then from the buffer to be sent to the channel adapter, and in the channel adapter to send it out. That is normally what happens in the other type of protocols. One of the things that was thought about in the InfiniBand was how to reduce the time that the packet will take from the application layer until it goes out from the server to the other side. That time has to be shortened. That time has to be cut. And this is something which is very unique to the InfiniBand protocol and InfiniBand environment. How do you make it more efficient? How do you make it more short? How do you make the latency better within this distance between the higher layer protocols to the channel adapter before it goes out to the other side? So this is also something that was a part of the thoughts of the guys that were behind the committee of the InfiniBand, behind the planning of the InfiniBand, like IBM, Mellanox, Oracle, HP Cray, Intel, and others that probably I did not count here. So the InfiniBand is actually a switch fabric architecture, interconnected technology connecting CPUs and IOs, which provides super high performance, which provides high bandwidth. Okay, starting at 10 gigabit per second up to 100 gigabit per second per port. Per port of a server, per port of a switch. The low latency that is required by your customers should be challenged by that protocol and should be responded by that protocol. And as I was telling you, the minimal latency that today's switch will add is 170 nanosecond. And the other challenge that I was talking about, how do we cut? How do we enhance the performance of the application and the way that it sends the information from the higher layer protocols until it goes to the channel adapter? And the main mechanism which is used for that, and I suppose all of you probably are familiar with, is using the process, using the mechanism which is called the RDMA. Remote Direct Memory Access, which will provide a better latency for every packet that goes from the upper layer protocol up to the channel adapter, and will also allow us to have a lower CPU or a better CPU utilization. Better CPU utilization because most of the traffic that was processed until the usage of the RDMA, that was processed in the kernel, now should not be processed in the kernel. This is one of the advantages of the RDMA. So traffic communication now, in the technology that we are planning, the traffic communication will bypass the operating system, will bypass the kernel, and it means that the CPU could be used for much more processes which are other than dealing with the traffic itself. InfiniBand was originally designed for large-scale grids and clusters. It came to increase the application performance. It can provide solutions for local area network, for bigger network, for storage area networks and application communications. It will provide high reliability cluster management. What does it mean, high reliability cluster management? Well, this is a bit vague, I must say. But the high reliability, of course, means that if you have something or an entity that will manage the network and that entity fails down, automatically you will have a backup to that entity that will take its place. We are talking about the first network, which is an SDN network, real SDN network, which means software-defined network, software managed network, which means that we don't need someone, we don't need an administrator that will configure all parameters. All the parameters in your network, all the parameters up to a level of a port can be defined today by the entity that manages the network by software. And that entity that manages the InfiniBand network by software is called the Subnet Manager. We are going, of course, to talk about it. Before we continue, since RDMA is one of the main processes or one of the main solutions here, what is the advantage of RDMA? RDMA, again, for those, well, somebody here does not know what RDMA is, and please raise your hand. Okay? So don't laugh if you have that question, it seems funny. There are people in the world which are not familiar with RDMA. Okay, so since everybody knows what RDMA is, then I suppose that you know that without RDMA, we have the application message that goes on the buffers on the user layer. And from the buffers in the user layer, they have to be copied. Every packet has to be copied to the buffers in the operating system level. And from the operating system level, after it is processed in the TCP/IP layers, it has to be copied again to the channel adapter layer. The channel adapter, or the NIC layer as it is called here, or as it is called in the InfiniBand environment, host channel adapter. So every packet has to go user, copy, kernel, kernel process, kernel copy to the channel adapter, and then goes to the other side. This is what happens without RDMA. With RDMA, we have a zero copy. We have a zero copy. We don't have to copy the packets, which are the data packets. We don't have to copy them to the kernel. We don't have to copy them to the kernel, so we save the time, we save the copy process, and we just take those packets directly from the user layer of one server. We send it directly to the user layer of the other server. And this is the RDMA over InfiniBand that saves time, saves latency, enhances the latency, and of course, allows us to do much more work in the operating system. This is actually, we can gain between 60 to 80% of improvement or efficiency, if you like, in the CPU. Because we don't need to process the traffic in the operating system, in the kernel. So let's look at the InfiniBand architecture. InfiniBand architecture, this is the basic structure. Like most of the other data network that you know, do you have the laser pointer working in your?
Yeah, it should be right there.
Probably. Okay. Data networks looks actually very similar. If you'll take Ethernet, frame relay, ISDN, X25, whatever data network, it will look like that, right? So we have to talk about the network itself and what are the parts which are special in those networks. So first, let's talk about our customers. Our customers are yours, your customers as well. Those are the HPC computing systems or computing servers and the HPC storage servers. So those are my customer. Here I have the application. Let's say that one of the more common applications in your environment will be OpenMPI protocol, will be GPFS, NVIDIA, or some other type of applications which are working here on your clients. Then we are taking that application, and that application calculation result has to go to the other computation server. In order to move the traffic to the other side, we have to take that packet, and then we have to go out to the other server. How do we go to the other server? For that purpose, we need switches. The switches are doing the switching, so we are taking packets from server number X to server number Y. Later, we are going to talk about addresses and addressing. So we are going to take the packet and send it via the network card of the InfiniBand environment. The network card of the InfiniBand environment is called the HCA, the host channel adapter. The host channel adapter has actually two sides. One side is the side of the bus of the server, which is the PCI bus, and the other side is the InfiniBand link. The InfiniBand link could go with the relevant media to the switch. What is the relevant media? The relevant media could be a copper. If you would like to have higher distance, instead of copper, you're taking fiber, right? Okay, so you took the InfiniBand link up to the switch. That switch may have different type of ports in terms of capacity. It could be a switch that takes 12 ports. It could be a switch that takes 648 ports. In order to move the traffic between that server, server A, to that server, server B, I have to go at least to one switch, and sometimes to several switches. So therefore, we are going into the network to between one switch to another switch, and then we send the information to the end destination. The data network, or the fabric, the InfiniBand fabric here, is working today in a subnet or one subnet only. The data network today is working as a layer 2 data network. What is the difference between layer 2 data network to layer 3 data network? Now, this is a question that I know that maybe some of you do not know. This is why I'm asking. Unlike RDMA. Yes?
Layer 3, it will do the switching using the IP packet.
IP packet.
Yeah, layer 2, it will do on the data network, either Ethernet or whatever.
Okay, well, of course, you are right about in part of the answer. Somebody would like to expand? No. Okay. So when I'm talking about one subnet, about switching of layer 2, switching layer 2 means that all of my nodes.
So the difference is routing.
Okay, so all of my nodes belong to the same subnet.
One local area network.
Right. Now, when you, IP is a term from another environment. Okay, because in the InfiniBand we have different types of addressing. Okay? So one subnet means that all of my nodes belong to the same subnet, Therefore, if you have 20 nodes or 2,000 nodes, all of them are part of the same subnet. And the switches currently here are switches of layer 2. So it doesn't matter of which organization here you are coming, today you are working with a layer 2 network in the InfiniBand environment. So those are our switches. About the addressing, we're going to talk in the next stage. So in most of your environments, you have the InfiniBand environment for the HPC, for calculation, for GPFS, for NVIDIA, for storage, for computing, edge storage, and most of it is InfiniBand. In some of your network, you have kind of mixed environment. And mixed environment means that maybe 2 years from today or 2 years back, you had another network that is maybe Ethernet network or fiber channel network. And sometimes you need to move information between the part which is the InfiniBand part, the InfiniBand environment, to the part which is the Ethernet environment. So you have two computers. One computer, one node is in the Ethernet environment, and one node is in the InfiniBand environment. How do you move traffic between two different environments? The answer is, how? Using routing. No. The answer is, thank you, by the way, for the response. The answer here is a gateway. It's not very far, of course, from the answer. The answer is a gateway. What a gateway is? A gateway is actually, if you like, a converter. A converter between two protocols. A converter between two languages. So what I would like to do here in my example, I would like to take a packet that is on a server here in that environment to a server in that environment. Because here they talk InfiniBand-ish. Do you know that language? And here they talk Ethernet. We have actually to take packets from the IB to Ethernet and from the Ethernet to IB. For that purpose, we have the gateway, and this is the job of the gateway, to enable us to talk between Ethernet to InfiniBand or fiber channel to InfiniBand. The component is called gateway. Is it clear? Usually, the information, or usually the type of packets, of course, that will go between the Ethernet environment to the InfiniBand environment will be IP packets. We are using, in the IB, we're going to talk about it, we are using a function which is called IP over IB. IP over IB, that will be the way we are going to take packets, IP packets here, and send them to IP packets on the Ethernet environment. IP over IP. Now let's talk about the management entity. One of the things that will make the InfiniBand environment special and unique is the capability of the InfiniBand to be SDN, software-defined network. And software-defined network, somebody here has managed Ethernet environment? Working with switches of Ethernet? Who? You're saying, you're nodding like Gabriel? So if you would like, for example, to change parameter in, on a VLAN or trunk or speed, what do you have to do? You have to do it yourself. So it's kind of do-it-yourself network, but you have to do it yourself. So you need an administrator in Ethernet environment. In InfiniBand environment, actually, as I was saying, it is actually the first network type that is SDN, software-defined network. So who is that entity? The entity in the InfiniBand protocol, that entity is called Subnet Manager, SM. The Subnet Manager is the most important entity in the network because it does all the configuration up to a level port of each one of the switches, of each one of the servers. Every parameter is managed by the Subnet Manager. This is the configuration. You don't need any administrator to do any changes here. The Subnet Manager will do it all.
It works.
It does work.
Sometimes, yes, most of the time. If it falls out and you don't notice that, you're in deep trouble.
We have a non-satisfied customer. So the way to do that today, in marketing, they're saying, you're right, Gabriel. What is the problem? We're going to solve it.
It's not that I'm dissatisfied. It's just, it's not just switching on the software and it's going to work.
Okay, first, let's talk about it. Okay? But we will do it in one of the next stages. Okay. So this is the subnet managers that are according to the theory and most of the time should work. And the subnet manager is doing everything. What happens if that subnet manager fails? If that subnet manager fails, let's call him the active subnet manager. If the active subnet manager fails, of course, we need another subnet manager in the network. The other subnet manager that will be somewhere here will be the standby or the fallback subnet manager. So we have, in every network, we must have a fallback and an active subnet manager. By the way, the protocol itself, or the standard itself of the InfiniBand, allows you to have more than 2 subnet managers. We suggest to have only 2 subnet managers in the network. So, we were talking currently about a layer 2 network, although it will support in the future in layer 3. The main components are the customer itself, the nodes, channel adapter that will allow you to do the network connection, the InfiniBand link itself that goes from the server to the switch, the switches that currently are doing layer 2 switching. The nodes belong, all of them, to the same network or to the same subnet. And in order to move packets between InfiniBand environment to other type of protocol environment, we have a functionality which is called gateway. Questions? Okay. So we talked about the different, elements. And first, the host channel adapter. The host channel adapter device that terminates the InfiniBand link. Here we have the connector. This is the host channel adapter. It looks like, I suppose, other channel adapters that you have seen up today. But the connector is different. The connector today in the InfiniBand is called QSFP connector. For those of you, I suppose, small number, who are not familiar with that, then a QSFP is a different connector. It's not SFP, it's not SFP+, it's not RJ45, it is QSFP. So we have a QSFP connector that goes out towards the switch. This is the channel adapter. Of course, it's part of the server. And this is the side that goes to the bus of the server, the PCIe bus. The PCI generation today that we are talking about is PCI generation 3. Then we have the switches. The switch is a device that moves packets from one link to another or from one node to another on the same InfiniBand subnet. On the same InfiniBand subnet, this is why we call it layer 2 switching. Okay? Then we have an element which is called a router. And now you can ask me, Oded, but you told us that we are working in layer 2 network. So why do you need a router? The answer is that currently, practically, we are not working with routers. Currently. We have router in the protocol, we have router in the standard. We have layer 3 for routing of InfiniBand. We have addresses for routing of InfiniBand. Routing will allow us to move traffic between one subnet to another subnet. So we have it in the standard, we have it in the theory. Currently, it's not yet implemented almost 100%. And then we have the gateway, or a bridge, as it's called, and the gateway job will be to enable us to move packets between InfiniBand environment to Ethernet environment or to fiber channel environment. We talked about the channel adapter, and we said that the channel adapter is connected with a link to the switch. The link could work with different type of speeds. It could be SDR, or DDR, or QDR, or FDR, at the end of the year, it will be also EDR. This is the rate, if you like. So if we are going back to 2001, the only capability was SDR, single data rate. Then we went to DDR, double data rate, and then we have QDR, quadruple data rate, and then we're going to FDR 14 data rate. This is the current generation. And at the end of the year, God's will, we're going to have the EDR, enhanced data rate. Yes?
I think it's actually 28.
What?
The EDR instead of 20.
25.
20 times 4 is 80. Yeah.
25. Sorry, it's a mistake. Well, please edit it in the thing. Yeah. Well, actually, it was put there intentionally to check if you are really checking what is said here. Right. Okay, so that was EDR. Let's now go to the addressing. When we talk about addresses of protocols, first we have the physical address. Each one of us has a physical address, kind of genes, I suppose, or whatever. The physical address in the environment of InfiniBand is called GUID. GUID is Global Unique Identifier of that specific node. So all the elements in the environment are nodes. Each node will have his own GUID. Who is a node? A channel adapter of a server is a node. A switch is also a node. Okay? A gateway is also a node. So each one of them is having physical address, which is a bit like a MAC. If you're not familiar with GUID yet, then you can compare it to a MAC. So this is my physical address, Global Unique Identifier. The Global Unique Identifier is an address which is comprised of 64 bits. Part of those bits, of course, will be the vendor ID. Okay? 64 bits. It is assigned by the InfiniBand vendor, and it is persistent through reboot. So if you're taking that channel adapter with its port, if the server goes down and up, the GUID is going to change. Yes? The GUID is going to change?
No.
No. Okay. That was right. So it is persistent. It is a fixed one. The GUID is a fixed parameter, fixed identification of the node. Now, this is for a channel adapter. So now here I would like to emphasize that point. Every port in a channel adapter has its own GUID. Do some of you have more than one port on the same server?
Yes.
Like 2 ports on the same server? Yes? How many GUIDs do you have for 2 ports? 1 for each port. Right. So this is obvious. So now, who is working with a switch with 36 ports? Your name? Sorry? Chris?
Yes.
Chris, how many GUIDs do you have to that switch? With 36 ports?
I think 1.
1 GUID. Right. So in a switch, you do not have a specific GUID to every port. The switch, you have only 1 GUID, or at least 1 main GUID. Let's call it a node GUID of the switch. So the switch has the node GUID. So how will we identify specific port in that switch? If you have 36 ports, how will you identify a port? Port ID, port number, exactly. So each port has a port number. So if you like to identify a specific port, you actually take the GUID of the switch plus the port number, right? There is another type of GUID which is called the system GUID. Someone is familiar with system GUID? Who has chassis switch or modular switch, which is more than 36 ports? No one here? You have? Which type of switch? Big fabric one. If you have a big fabric one, it means that on the same chassis, on the same physical chassis, you have actually multiple switches. So each one of those switches will have its own node GUID. But the chassis as a whole will have another GUID, which is called a system GUID. So the system GUID will be the identifier of the whole chassis, and each one of those switches within the modular will have a specific GUID. Okay, IB Fabric. IB Fabric basic building block. When you have InfiniBand Fabric, InfiniBand Network, that InfiniBand Network is built according to the needs. What is the basic need usually? The basic need will be the capacity. How many nodes do you need in your cluster, right? Of course, this is only one parameter. So when we are talking about the Fabric basic building block, each one of those blocks is going to be a switch. By the way, each one of the switches is based on an ASIC. What is the ASIC? Actually, the ASIC is the heart of your switch. The ASIC is a switch. The ASIC is a chip. The ASIC is a switching chip. And today, in this generation, every ASIC has 36 ports. Why do I say this generation? Because if you're looking at 2004 or 5, the ASIC, the basic ASIC, was actually structured of 24 ports. Today, the ASIC is 36 ports. When you build a network, the network is built according, again, to the number of nodes that you have to provide, that you have to support. It could be a network, for some of you, you have, I suppose, 100 nodes. Some of you might have 600 nodes. Some of our customers have 10,000 nodes. 10,000 and more. So of course, the number of switches that you will have to provide will be a different number according to the number of nodes that you will have to connect. Okay, here, let's look at that slide. Everybody can see the slide even from the last lines, I hope. Okay, so every switch here, let's take a basic switch in our cluster. And as you can see, the nodes are connected. The nodes are connected to switches. The switches that are used for that direct connection, the direct connection to the nodes, those switches have a name. Does somebody can tell us what is the name of those switches? Leafs, exactly. Those switches are called the leafs. Okay, so the nodes, the servers are connected to the leaf switches. Each one of those is a leaf. Now let's say that in that example, as you can see, every leaf is going to be connected with 18 ports to 18 nodes. So 18 ports of that leaf, and 18 ports of that leaf, and 18 ports of that leaf, and so on. So if you are using 18 ports from the leaf to the nodes, what do you need the other 18 ports for? So I have 36 ports, 18 are used for the connection to the nodes themselves. What do I do with those 18 ports? Trunks. Okay. The other 18 ports are actually used as connections to the next layer. The next layer in the fabric is called how? How do you call those switches? Core, yes, or it has another name? Backbone, also spine. Spine switches. So we have two basic type of switches. We have the leaf switches, which are connected directly to the servers, and we have the spine switches. And the spine switches have one main job. The spine switches will help us to make interconnection between servers that do not belong to the same what? Leaf, to the same leaf. Because let's say that you have those servers here, servers that belong to leaf A, and here you have servers that belong to leaf D. How will you connect between those servers to those servers? The answer is you need another layer. That layer will allow you to make interconnection between different leaves. You would be able to move packets between that leaf to that leaf via that spine. Okay? So this is the spine layer. This is the job of the spine layer, to allow connections between traffic that goes or belong to different leaves. Now, if you paid attention, I took 18 ports to the servers, and then I have 18 ports that are going to the spine switches. So actually 18 ports towards the servers and 18 ports towards the spines for interconnection. Why did I take 18 ports here and 18 ports for interconnection? Yes?
Maximize the number of nodes you could connect with two layers.
At the same time. Right. So actually one of the things you would like as HPC customers, you would like the network to be non-blocking network. And one of the ways to get close to that target is that if, for example, you have 18 nodes or 18 servers, in order to verify that they will get the bandwidth that they need when they want to send out the information to other 18 servers, you would like to have the same bandwidth of the nodes will be supported by equal bandwidth in the interconnection fabric. So if you would like to move 100 gigabit per second from the nodes, you need 100 gigabit per second in the interconnection environment to support it. So actually, if you have a number of 18 ports of FDR to the nodes, you will need 18 ports of FDR in the interconnection. If you have 72 ports of FDR to the nodes, you will need 72 ports of FDR in the interconnection. In that way, you will enhance the chances that every time you will have bandwidth that is required from a node to go out to another server, you will have that bandwidth in the interconnection environment. This is called non-blocking, or if you would like, virtual or semi-non-blocking in the interconnection environment. Now, of course, it's not a total proof. It's not 100%, but this is one of the rules that we use in order to have kind of semi non-blocking environment. Of course, we could have taken, instead of 18 ports here and 18 ports in the interconnection environment, we could have taken, for example, 27 here and 9 here. Okay, what happens if you have 27 ports here and 9 ports that are going to the interconnection? You have actually a different ratio between the interconnection ports to the connections that are going to the servers. And the different ratio means that you have higher number of node ports than ports of interconnection. You will get a blocking ratio. Okay, let's go to the next one. If you have questions, please ask me. Yes, please.
Question. Why do the basic blocks have 36 ports, not, for example, a power of 2, not 32?
Why the switches do not have a different number?
Why this choice? In this case, you have basic blocks having 36 ports.
Okay, the reason is
36.
the reason is that the integrated circuits which are produced, the ASICs which are produced, the basic ASIC today has 36 ports. Although, I can tell you that we also have a switch of 12 ports, for example, which is also a possibility.
Okay, this is clear because of the hardware, but
Exactly.
of 36, when ASIC was designed, why 36 was used?
I'm not sure. Can't tell you.
Possibly to be able to choose the ratio of battery versus body.
I can tell you that the previous generation was 24.
Well, you have, it's divisible by 1, 2, 3, 4, 6.
You're talking about the flip-flops inside and so on, I suppose. Anyway, this is the structure. This is the internal structure. Okay, so in that example, we have actually a fabric that will support 72 ports or 72 nodes. Why 72 nodes? Because we have created an environment that has 4 lifts. Each one of the lifts has 36 ports, and among those 36 ports, we have 18 ports to the nodes. So 18, 18, 18, 18, it's 72 ports towards the nodes, and then we have 72 ports which are providing us the support in the interconnection environment. Question? So we have 4 chips which are function as lines or lifts, and 2 chips which will function as cores or spines. Okay, so that was the main structure of the fabric. Let's go to the next stage. We talked about the physical address that we call the GUID. Let's go to the next stage. When we are moving traffic between one node to another node, we need to have an address. The address which is used is a layer 2 address. So when I would like to talk with Chris, or when I would like to talk with Gabriel, each one of them will have a layer 2 address. The layer 2 address in InfiniBand environment is called LID, Local Identifier. This is the LID. The local identifier, it has 16 bits. 16 bits, it means that the range that is supported could be up to 2 by 16, which is about how many addresses? About 65,000, right? Yes, this is the layer 2 address range. Who is providing the addresses? Well, one function. This is the Subnet Manager. Each one of the nodes in this room is going to get a lead provided by the Subnet Manager. The lead, again, is called Local Identifier. So each one of your servers has 1 or 2 leads. It depends on the number of the ports that you're connected with. It is assigned by the Subnet Manager, and it is theoretically not persistent during reboot, theoretically. Why do I say theoretically? If I will give you the option, what do you prefer? Would you like it to be changed every reset of a server? What? Who said no? No. Yeah, you wouldn't like, you will prefer your network, you will prefer your fabric to stay as stable as possible. You would like that if Chris would like to call Gabriel, even if Gabriel went down because of some issue even in this case, when he comes up, we would like him to stay with the same lead. So of course, there are parameters that will allow you to say that even if a server goes down, we would prefer that when he comes up, we would prefer him to come with the same layer to address, with the same lead. When we talk about the lead addresses, we have two ranges of addresses because we have two types of communication in the InfiniBand environment. The first type of communication in InfiniBand environment is a unicast communication. When I talk with Gabriel, only two of us, this is unicast. When we talk here in the room and everybody hears, this is what? When I send information to a group of listeners, is it unicast? What is it? It is multicast. Of course, somebody will ask, yeah, but it's like a broadcast actually. But in InfiniBand, we do not have broadcast. In InfiniBand, we have only multicast. And the simulation, if you would like to do like a broadcast, you will actually create a multicast group that will include all the participants. So in InfiniBand, there is no broadcast, only multicast. So if you talk about the specific addresses, you have a unicast address range, which is between 1 to BFFF, and you have a multicast range, which is between C001 to FFFFE. These are the lead addresses. Who provides the leads? Subnet Manager. Okay. The next element that I wanted to show you is that. So, as I was saying, we have only one subnet in your organization. Most of you. One of the questions will be, and it might come from you, so what if we would like to have different departments or different customers in our organization, in our network? How can we do that in InfiniBand? We know how to do it in Ethernet. How do we allow different departments to have their different kind of environment in InfiniBand? We have only one subnet. Can I ask if some of you in his environment has such a need? Or thought of such a need, or knows what the solution is? Well, since there is no answer, I will answer myself. I will ask and answer. So the answer will be partitioning. Partitioning is the way that you can actually implement in your environment, on your InfiniBand Fabric, in order to define different partitions for different customers. You may have the red partition and the green partition and the blue partition, which all belong to the same subnet, but their packets have different color. Actually, it's called different identifier, and that specific identifier is called partition key. Partition key, okay, is actually the identifier of every different partition. So now you can say I have the storage guys, I have the open MPI guys, I have other type of guys, IP over IP guys, and I would like to have them on a separated environment, although all of us belong to the same subnet. That is called partitioning. So that partitioning can help us to provide different environment to different applications, or different environment because of security purposes. Because, for example, in your institute, you have two researchers. One of them is for university, and the other one is for Boeing or Airbus. And the research for Airbus, the Airbus guys who are paying money for that, they are telling you, we wouldn't like to have our part of the network to have the packets touch with the other common people packets. Can you separate them? The answer is yes, partitioning. The packets of the red environment will have packets or partition key ID 2, and the green environment will have partition key ID 3. This is not the only thing. The other thing that you can have with partitioning is quality of service, which could be different. Could be different. It's not the only tool, but it's one of the tools that will allow you to provide different quality of service to OpenMPI and other quality of service to GPFS. Why? Because I might place them on different environment or different partition.
Let's stop there.
Yeah, okay, let's stop there. Let's stop here. We'll have some a coffee break, and we will continue in
15 minutes.
15 minutes.